All right, I got the thumbs up that I can introduce Anna now. So normally when I introduce our very special speakers to the Centre for Climate Science's distinguished lectures, I don't need cheat sheets because I can kind of memorise their background and their accomplishments. Anna's accomplishments are so long that I have to read some of these, and a recognition also is long. So I'm just going to just sort of cherry pick a few of these because otherwise I'll take half an hour of your time, Anna. But Anna's, as you may well know, is the founding director of the Climate and Resilience Hub at Carnegie Institute for Sciences, and she also holds some joint appointments in some academic departments at Stanford. She started, I guess your academic career started as associate professor at Michigan in Ann Arbor. She told me she was sort of trained as an environmental engineer, did stuff to do with water, presumably water on the ground, right, in environmental engineering, shifted to the carbon area, and of course, you know, she's been very active in that, and engaged, and obviously her desire to come and visit us today, we are able to twist her arm and come and visit us today. Her desire to visit us today was a sort of reflection on the great carbon stuff going on in JPL to some extent. She's sort of going full cycle back, almost, not quite, but full cycle back to begin to start looking at water issues again, and that's what her talk's going to be on about today. She has served on many important committees. The most recent one she was co-chair of the midterm review of the decadal survey, and that report will be coming out any day we're here, but my guess it's going to be in the fall. Dwayne thinks it's going to be in the summer. I'm betting the fall. We'll see who's right and who's wrong. Yeah, all right, okay. She's received early career awards from NASA, NSF, and also has received the Simpson Medal, when named after the great woman scientist of the earth sciences, Joanne Simpson. So this is sort of great recognition, and so it's fantastic, Anna, that you could carve out some time. I know you're visiting Caltech this week, and we were able to twist her arm and come and spend a day with us, particularly with the carbon folks, and to give an important distinguished climate lecture. I won't read the title. I'll leave you folks to read it. And Anna, it's all yours. Thank you.
Thank you so much. And I think I turned on the mic correctly. Yes? Yes. Perfect. Well, thank you so much for the introduction. It's really a pleasure to be here. And as Graham mentioned, I'll actually be around all week. Most of my time will be at Caltech, but if folks want to meet afterwards, then I'm absolutely happy to do that. And what I decided to do is, as many of you know, I've had the great pleasure of collaborating with folks at JPL on questions related to the global carbon cycle for almost 2 decades at this point. And so what I thought I would do instead is actually tell you about some of the work that we've been doing on the climate water quality side, because that's an area that I would say we spend close to about half of our effort on, and that has, I think, great opportunity for collaboration with some of the great work going on at JPL, but that for reasons that I'm not quite sure, we haven't quite intersected on that yet. So I'm just going to take today to give you a very high-level overview of the types of scientific questions that we're interested in, how that all came about, and what we've been doing recently. And I'm hoping that this will seed then additional conversations and potentially follow-on collaborations as well. And so the title of my talk is on assessing climate impacts on inland and coastal water quality. And to set the context for this, I pulled this diagram from the latest IPCC AR6 synthesis report that was released just last year that presents some of the adverse impacts from human-caused climate change that will continue to intensify. I'm just going to put my watch down so I can keep track of time. And really what I want you to notice is 2 things. Many of these have to do with water. So anything ranging from physical water availability to flooding, to agricultural ecological drought, global sea level rise, and so on. But what's striking to me is that, at least on the face of it, almost all of these have to do with questions related to water quantity. And I would argue that if we're going to be thinking about water sustainability, really we need to be putting water quantity and water quality on an equal footing. And so if I were to summarize what my group's goal is in the area of the water research that we do, is to try to put questions related to climate and water quality on an even footing with the sophistication with which we have come to understand the relationship between climate and water quantity. To give you a glimpse, we primarily look at these questions through the lens of eutrophication, harmful algal blooms, nutrient pollution. These are 3 images of massive harmful algal blooms that all occurred in the 2014-2015 timeframe. The first one was this massive bloom on the western coast of the continent that went all the way from Mexico to northern Alaska, shut down fisheries, caused impacts to marine mammals and so on. The second one is an image from Lake Erie, where you can see, actually let me go back just by one image, harmful algal bloom that stretched hundreds of kilometers across the lake. Just for scale, this is the city of Detroit here, so you can really see how big that was. And then the last one is off the coast of Florida that now sees annual impacts from coastal harmful algal blooms. And this is not just a scientific issue, it's also, of course, a societal, a political, and economic issue. And so this is my favorite cover ever from an article at Political magazine talking about how red and green slime could swing Florida's Senate race. And so really it's a very timely question as well. Scientifically, the context for the work that we do is that traditionally, water quality has really been thought of primarily as a local or regional issue. And so you might contrast this type of situation where you have, let's say, responsible development, agricultural production, and land use that then has a healthy aquatic ecosystem, plenty of oxygen in the water, in contrast to what you see on the left, where you see a different type of landscape where there is much less control on nutrients entering waterways, resulting in excessive phytoplankton blooms or harmful algal blooms, potentially then also hypoxia or anoxia, leading to other ecosystem impacts. The question that we've been asking is, to what extent is this view an incomplete view? So in other words, to what extent is water quality not really just a local and regional issue, but really also an issue that is impacted by human activity at the global scale via global climate change? And really, my interest in this work started in 2011, or maybe a year or two before 2011, where there was this massive, record-breaking harmful algal bloom in Lake Erie. This is an image from MODIS, and both the spatial extent and the biomass associated with this bloom was roughly 2.5-fold greater than any previous bloom that had been observed in Lake Erie. And it just so happened that we had a brand new, large NSF-funded project that was focused on climate and the Great Lakes ecosystems. And so we assembled this really large team that came together and wrote this paper that ended up being published in PNAS, where we assembled a series of models to try to assess what was it that made that particular bloom as intense as it was? And was this just a freak accident, or was this a premonition of what blooms might look like under future conditions? I won't go through this in detail because this is now already 10 years ago, but at a high level, we looked through a number of hypotheses that had to do with land use in the region, agricultural practices, meteorology, how those might impact different components of the system. And we systematically use different inventories or models to assess each of these hypotheses. And at a high level, all the ones where you see check marks are ones where trends were in a direction that were consistent with the bloom in 2011 being particularly intense. And then we also looked at future conditions, and all the ones you see with a red square are conditions that we would have anticipated to become more prone towards large blooms in the future. And so then the paper, as the title implies, was that we concluded that this bloom was caused by agricultural and meteorological conditions that were also consistent with expected future conditions. And this was wonderful, But at the same time, it was not fully satisfying. It felt very qualitative in that we had this, again, the smorgasbord of models, each of which was assessing one type of mechanism, and all we could really say is, are things trending in a direction that is consistent with what we observed? And so a lot of what we've done since then is to try to substantiate this in a more quantitative way. And I'm going to structure the rest of the talk around what I would say are the four main points from this piece that was published in 2016, where I tried to think through why is it that we are so much further behind in understanding water quality and climate relative to where we are in terms of understanding water quantity and climate. And I made the case that there's really four reasons for this. The first is that the linkages between climate and water quality are, first of all, very poorly understood, and much more so than in the case of water quality. Second is that the role of climate is often very difficult to pinpoint because you have this delicate interplay between human activities at local, regional, and global scale. So it's obviously not just the local activity that matters, but it's also not just the global activity that matters. Third was that often the observational evidence to underpin a long-term view is lacking because very few systems have long-term in situ monitoring. And as everyone in this room knows, the remote sensing capabilities are not always as mature as they could be. And then lastly, just that the spatial temporal scales that hydrologists and aquatic ecologists have tended to focus on historically are very different from the types of scales that climate scientists have focused on, and that is a challenge as well. And so this is maybe quite a few words, but really it comes down to, can we figure out what actually happened? Can we figure out what caused it? What the future will hold? And very importantly, can we scale up from a few very well-studied systems to a much broader set of systems that describe conditions in general? And so really what I'm going to do for the rest of this talk is give you a few snapshots of how we have started trying to nibble away at some of these questions, specifically in the context of nutrient pollution and harmful algal blooms. And what I'm interested in doing longer term is to continue to work at these questions. And I think especially given the focus of groups here at JPL, there's a tremendous amount of opportunity for interfacing across these questions as well. And so first, if we think back to this Lake Erie example that I gave earlier, one of the things that we try to understand is, can we get a better understanding of what has been the history of harmful algal blooms in Lake Erie and what has caused both interannual variability and these exacerbated conditions in more recent years? And when we started this work, all we really had from a remote sensing perspective was a 10-year record from MERIS that went from 2002 to 2011. And it's very, as I think you probably know, you can't really identify a climate or a long-term signature if you're only looking at 1 decade of data. We need a minimum 2 decades, ideally 3 decades of data. And so one of the first things that we did in this work, and this was work led by Jeff Ho, who's a PhD student at the time, was mine the historical Landsat record to see if we could actually extend our understanding of the historical conditions in Lake Erie to go back further. And so to do this, Jeff developed an approach to mosaic observations from Landsat. I won't go through the methodological details here, but I invite folks to look at the paper in RSC if you're interested. But to make a long story short, we were able to develop an algorithm that used Landsat to essentially replicate the data that we had for MERIS for the most recent decade at the time. And we did this by using a whole slew of both in situ and remote sensing observations and a whole slew of metrics that we had at our disposal. But the short answer was that we were able to then extend the record of harmful algal blooms in Lake Erie all the way back to 1984. And once you're at that length, what we found is a really shockingly simple answer to the question of what was happening. And really, 75% of the variability over a 3-decade period was explained by 2 very simple variables. The first, not surprisingly, in blue is the springtime loading of dissolved reactive phosphorus. So this is springtime loading phosphorus into the lake. This is what a lot of existing models had been based on. But second, in orange, was the essentially decadal scale cumulative loading of reactive phosphorus into the lake that really suggested to us that there was a lot of internal recycling of phosphorus within the lake from the lake sediments that hadn't been acknowledged or seen at that point, but has been confirmed by subsequent studies. And so what you can see then in this plot is how this orange component of the plot, which is, again, in this particular case, this 9-year cumulative loading, combined with the year-to-year variability in blue, tracks the history of harmful algal blooms in Lake Erie. And if you look at 2011, which is this big green bar here, you can see how it's not just about loading that particular year, but really this accumulation of loading from previous years as well that explained what we saw. And so again, springtime and decadal dissolved-reactive phosphorus explained this 30-year history of blooms in Lake Erie. What was really interesting is that the dominant populations of phytoplankton have changed in Lake Erie over this time, and yet this relationship has remained robust, which was an unexpected surprise. And so unlike when we wrote this original paper that I talked about before, where really what we had were simply a list of hypotheses that were either consistent or not consistent with what we observed, once we had the 30-year history, we could really quantitatively demonstrate that it's this both short-term and long-term history of surface runoff and nutrient loading that was really the predominant cause of what had happened in Lake Erie in 2011. And then in 2015, which was the subsequent yet larger bloom that was observed there. And so I would say that at least for that one particular example, we successfully answered this question of what had happened historically, which then allowed us to answer this question about what had caused it. But then we get back to this question of, can we scale up? In Lake Erie, we're lucky in that it's a very actively studied system, and so there was a lot of in situ observations that we could use to support our modeling efforts. And so what we wanted to see next is, could we scale up in two ways? One, in terms of observing what is happening in lakes globally, and second, what is actually driving changes in nutrient loading at larger scales as well. And so the next piece of work we did on the first question is we actually took this Landsat-based algorithm that we had developed for Lake Erie, and we applied it now to dozens of lakes globally that were large enough that we could get reliable Landsat data. And what we found is that bloom had become more intense in over 2/3 of the lakes that we were able to see. And this was important because at the time, this is just a few years ago now, there was this big debate as to, are blooms in lakes really getting worse, or is it just that we're paying attention more? And there hadn't been a study that had looked at dozens of lakes globally to try to differentiate those two hypotheses. The second thing that was interesting about the study is that we took these lakes and we grouped them into essentially these 4 prototypical histories where we had sustained improvement in conditions over the 3 decades, improvement and then deterioration, deterioration, and then no significant trend. And what was interesting is that there was only one thing that was consistent across all the lakes that had sustained improvement in conditions, and that these were the lakes that had warmed the least. And so despite all kinds of differences you might see locally in terms of, let's say, wastewater treatment, agricultural intensification, a variety of other factors, the one consistent factor is that the lakes that warmed the least were the ones that were able to sustain improvements in water quality over the 3-decade period that we looked at. The second part of scaling up that I just mentioned is, in the Lake Erie study, we showed that it was the phosphorus loading into the lake that was driving the blooms. But the natural next question then is, well, what is actually driving the nutrient loading itself? And so to answer that question, we've now done a series of studies, but I'll show you some highlights from one, where we looked at what have been the changes in nitrogen loading across the continental US, and how do those map onto local human activity versus global human activity? And so what we did here is take data from a large number of catchments that are routinely monitored as part of the Linkages data set maintained by the USGS. And we took data from those catchments and used very simple variables such as temperature, total precipitation, extreme precipitation, land use, nitrogen application rates to try to derive a very simple statistical model that could represent annual scale nitrogen loading in these catchments. It turned out to be what I always call an embarrassingly simple model, in that if you just account for annual precipitation, springtime extreme precipitation, land use, and anthropogenic nitrogen input, and springtime temperature, you could explain well over 3/4 of the variability both in space and in time across these very diverse regions across the US. And using that, we were then able to represent nitrogen loading for all Huck 8 scale watersheds across all of the US over the last 3 decades. You see some things that might not be so surprising, and so increasing nitrogen loading in regions associated with the agricultural Midwest, and then not much happening in the desert Southwest, and perhaps maybe a more unexpected reduction in loading in the South. But because this was based on this very simple model, what we were able to do next is to actually break apart this overall signal into its component pieces. And that's what I'll illustrate here on the left at an aggregated spatial scale, just for visualization purposes. So this first map is exactly the same as this original map, just at an aggregated scale. But what was interesting is if you break down this overall signal of increased or decreases in nitrogen loading in the rivers in these different regions, much more of this trend in nitrogen loading actually came from climatic variability. Much less actually came from changes in nitrogen inputs. And to me, this is really important because whenever you have these water quality outcomes, the first knee-jerk reaction is to often blame the agricultural community. And there's this dynamic that is set up about environment versus food production and the disparity between their goals. But really what we showed here is that the majority of what we've seen in terms of changes in nitrogen loading are really attributable to changes in climate. And if we take it one step further, it's really changes in precipitation patterns, both in terms of the total annual precipitation and the extreme springtime precipitation that have led to what we have seen. And here you see it broken down one step further. And so the take-home message here was that annual precipitation, extreme springtime precipitation, and springtime temperature are the primary drivers of trends in nutrient runoff.
How do you measure the nitrogen input?
I'm sorry?
How do you measure the nitrogen input?
So if I go back just a couple of slides, so at these locations, the original input, there are inventories of nitrogen inputs. So in this particular case, we use something called NANI, which is the net anthropogenic nitrogen input, that tracks all the different mechanisms, whether it's agricultural production or food export, and essentially produces these estimates at this watershed scale, typically at 5-year intervals. And that's what we use for the inputs of nitrogen. In more recent studies that I'll show, we use another data set that's more of a nitrogen surplus inventory, but they're inventory-based methods. And then the observations are then observations from this Gauges data set. And so at all the points where you see the black dots, these are monitoring locations at the outflow of these catchments. And what I'll say is that what's actually monitored is discharge and concentration, but then you can use those to infer actual flux of nitrogen and to gap fill between the concentration measurements as well. Jim?
Did you look at to see if there's a correlation between the nitrogen and the climate factors, just in case farmers change their practice during dry or wet years? Do you see any kind of correlation there?
I don't remember what the actual correlations were, but they were not high. Also, between those two particular factors, but certainly for things like the annual precipitation and the extreme springtime precipitation, those two variables would be much more correlated to one another. The statistical approach that we use for building the model has this weighting between model complexity and explanatory power through the Bayesian information criterion, so that additional variables, if they are partially correlated to the ones you already have in the model, only get added if the amount of additional explanatory power that they provide is sufficient to offset the increased complexity of the model. So the model selection process in of itself partially takes care of that. Yeah, I'd have to go back and look at the numbers for the correlations, but I don't believe there was any strong correlations. You know, for some of these variables, I have to say, in the net anthropogenic nitrogen input, some of those are only available on a 5-year interval, so we had to interpolate in between. Some of them are available on annual scale. So I think there's a limit even to the degree to which we could capture that year-to-year variability in farmer behavior that you're referring to.
Yeah,
So,
I don't want to derail you here. I'm just curious, like, what do you expect?
hang on. I was remiss. Any questions from the room have to go through the mic because this has been recorded.
Or I can repeat them.
Or
It's maybe
or you
the
can
easier way to do it
or you can
also.
repeat that might be more expedient.
Yeah.
Questions from the audience who are out in the ether. We're going to pick them up from the chat at the end of the seminar. I should have announced this at the beginning, but I sort of forgot. So any questions, go through the mic so they can be picked up and recording. Okay? It's my fault.
And I'll say that in the first study we wrote on this, which is this 2016 study, which predates this one, we looked more at spatial variability and interannual variability. And in the spatial dimension, absolutely the main determinant is nitrogen input into the land. Here what we're looking at is that long-term trend behavior where it seems to be more related to these climatic factors. Okay. We did a similar or related study in India as well, which turned out to be very interesting. There's a lot less data, or at least it's a lot more difficult to get at detailed data for India. And so what we did there is focus on the 7 major river basins within India rather than individual watersheds. And what we found there, which was both very surprising and at the same time somewhat consistent with what we saw in North America. So let me orient you a little bit with this plot. So if you just focus on the left-hand side plot here, each of the 7 major river basins has its own color. The loading from each of these basins in each year of the study has a dot, and the ellipses represent essentially the range of interannual variability for one particular basin versus another. What you have on the horizontal axis is total annual precipitation, and on the vertical axis you have dissolved inorganic nitrogen flux. And so the first thing to notice is both within individual river basins as well as across the basins, this very clear relationship between total annual precipitation and dissolved inorganic nitrogen flux. And so again, this very strong signature for precipitation, variability in the monsoon from year to year. What was very surprising to us is if you do the same analysis with fertilizer application rate, we saw for most basins very little signal, both in terms of variability across the basins as well as interannual variability within a basin. And this was absolutely contrary to what we were expecting because as you all know, there has been this very substantial intensification of land use and agricultural production in India. And we were expecting to see this in the water quality data coming out of these major river basins. And given this, the hypothesis that we ended this particular study with is that most of that excess nitrogen must currently be ending up in the groundwater rather than ending up in the riverine efflux of nitrogen. But if you look at future projections of nitrogen application rates from integrated assessment models, you can see how this intensification is really going to continue very strongly, both for India and for Southeast Asia in general. And so I certainly would not necessarily assume that this pattern that we saw for the historical data would necessarily continue out into the future, but this was an interesting conclusion and consistent with the North American study in the sense of showing this very strong role for really a climatic signal in what we think of as a water quality outcome. Okay, and so these last couple of studies that I showed you really had to do with the ways that we have been working to use data from a relatively small number of well-studied systems or basins to try to make conclusions at scales that then mesh more easily with the types of scales that we tend to think of from a climate science, climate mitigation, or climate impacts perspective. And so then the last set of examples that I wanted to talk about today is then, well, what can we say about what the future will hold in terms of some of these processes that we've looked at? And again, I'll just show you a couple of snapshots of studies that we've done recently. The first is one that just appeared last year in PNAS, where we had additional data from more recent years, and so we were able to augment that original set of catchments that we had used in the study of historical nitrogen loading that I just talked about a few minutes ago. So we had 123 catchments in the previous study, and we were able to add over 100 additional ones. And in doing so, we were then able to go from what had been a linear model to now a more sophisticated nonlinear model, where one of the interesting things that came up is that while, so again, let me orient you. You have, in this particular case, total annual precipitation on the horizontal axis, temperature on the vertical axis, and the colors are contours of nitrogen loading at the watershed scale, holding all other variables in the model constant. And what you see, which is what I wrote in this box here, is that while increases and total, and I'm not showing it here, but also in extreme precipitation, lead to increased loading, so things get more red as you move from left to right, this effect actually slows at higher precipitation rates, whereas the impact of warming becomes more apparent as warming continues. And so what that has meant is that if you look first at these bar plots here, for all three of these regions that I've highlighted here for the continental US, you have changes in precipitation that are associated with either increases in total precipitation or increases in extreme precipitation, tending to lead to increases in nitrogen loading, while at the same time you have warming leading to decreases in nitrogen loading. And that could be through a variety of mechanisms, such as increases in evapotranspiration or increases in denitrification rates. But in a variety of ways, you always have these two factors playing against one another. And I'm not sure if you noticed that in the previous study that I showed for the previous decades, but you had this trade-off as well. So all of the plots that had to do with precipitation were orange, so increases. All the plots associated with temperature were blue, so decreases. But in the historical period, the changes in precipitation were winning out. And so overall, what we saw for at least a large chunk of the US is increases in nitrogen loading resulting from changes in precipitation that have already occurred. What we're seeing here, for large parts of the US, so everything that is in yellow, these are now bar plots that span across the ensemble of CMIP6 climate models looking out into the mid-century, is that for most of the country, we think that going forward, the opposite will happen, that this impact of temperature will outpace the impact of precipitation, such that you might actually see decreases in overall nitrogen loading. This is not the case everywhere. So if you look at just the green regions, because the changes in precipitation will be more pronounced, they will still, on average, continue to outpace the impacts of warming. And then you have this region in blue where you're actually either seeing no changes in precipitation or actually drying in the coming decades. And then, of course, you've got both the precipitation signal and the temperature signal pushing towards decreased nitrogen loading. And so what's really interesting here is that what we're expecting, based on this most recent study, is that the net impact of temperature and precipitation both varies by region, but that on average, what we will see in the future is likely to be the opposite of what we have seen in recent decades. Another study where we've looked at future impacts is we were curious about how will climate mitigation efforts impact eutrophication? Because of course in the US, it's not just that precipitation and temperature will change, but many other factors will change as well. And so what we did in this particular study is we looked at integrated assessment model runs that were done in support of the CMIP6 climate model intercomparison effort. And as part of those integrated assessment model runs, we had access to information such as land use change, land cover change, food production, nitrogen application rates, and so on. And so we were able to look at what will be the impact just of these different approaches at climate mitigation across these SSP scenarios on the water quality outcomes that we were interested in. And so here I'll show you specifically the contrast between two different scenarios, SSP1 and SSP4, both of which achieve quite substantial climate mitigation in that they are associated with relatively low temperature increases, relatively quick reductions in greenhouse gas emissions, but do so in very different ways. So for those who are familiar, you know that SSP1 is this quote unquote sustainability road where we really do this through conservation and energy transition to renewable resources and so on. Whereas SSP4 is this one that's termed inequality or a road divided, which instead relies very heavily on biofuels. And so, not so surprisingly, I think from a qualitative perspective, but we showed it here. This is very strange. I have to point here. You see very different outcomes in terms of the degree of nutrient pollution that's observed for two different scenarios that might otherwise have looked similar to each other if you were looking at them purely from a traditional climate outcomes perspective. And so in the case of SSP1, you see that for the continental US, there's very little overall change in nitrogen loading over the coming decades. And you see this MARB region is this region that's outlined in black, and the Northeast is this region that's outlined here, versus this SSP4 scenario, which again is not that different in terms of temperature outcomes and precipitation outcomes, but dramatically different in terms of water quality outcomes. And so the conclusion here was that societal choices about climate mitigation will really substantially impact riverine total nitrogen loading and therefore water quality outcomes more broadly. But that there are pathways that allow you to limit climate change and eutrophication concurrently. And the argument is then that really in thinking about climate mitigation, we need to be thinking across a much broader set of outcomes rather than the climatic outcomes that we're used to thinking about traditionally in the IPCC context. Okay, and then last one. This is, again, a very recent study that just came out in Nature Water last fall, where we were interested not just at overall magnitude of nitrogen loading or of harmful algal blooms, but we were interested specifically in toxins in lakes, and especially a toxin called microcystin, which is a hepatotoxin, so attacks the liver and is quite widespread across the US and elsewhere. And so what we did here is to represent the risk of exceeding various thresholds of microcystin concentrations based on a data set from the National Lakes Assessment, which is a database put together by the EPA, where every 5 years they go out and sample a few thousand lakes across all of the US. And we took the data from this National Lakes Assessment, and we again looked at what are the factors that help explain both the spatial variability in these data as well as the interannual and longer term variability in these data. And so first of all, maybe not so surprisingly, we found that the upper Great Plains and the upper Midwest show the highest probability of exceeding a variety of microsystem thresholds. This 0.3 threshold that's shown here is the threshold for safe water use for children. And we use that other thresholds as well. And the underlying statistical model that we developed across all of these lakes showed for the first time that for microsystem, if you look at the absolute change in the exceedance probability, you actually see this temperature optimum around 25 degrees centigrade, so that the risk increases as waters in lakes warm, and then the risk falls off again at higher temperatures. And so really the highest risk is around this 25 degrees centigrade level. But what's really interesting is that these various lines that you see here are lines of different in situ nitrogen concentrations. And so this impact of temperature is itself very sensitive to nutrient concentrations in the water. And so in those regions where you have high nutrient concentrations and you experience warming, then the impact on the risk associated with high toxin concentrations really goes through the roof. We then use this model again with the CMIP6 climate model archive. Here I'm just plotting absolute difference to 22 degrees centigrade, which is where that absolute peak was. If you squint a little bit more, the peak here in terms of maximum risk. And so you can see even visually here, we're plotting here then difference to 22 degrees centigrade. So you can see how historically these are the regions that had lake water temperatures that, all else being equal, are at highest risk of high toxin concentrations, and how even at present this band has moved north, and of course by mid-century and late century will continue to move north, whereas interestingly some regions in the south will now be too warm for that optimum, and so you might actually expect to see a falling off in the risk of high concentrations. And so this is also what you see here then. This is now the relative change in the exceedance probability of these water quality thresholds. And so this is just a difference from the historical period to the present, mid-century minus historic, and then late century minus historic. And so the conclusion here, which is in this box here, is that the regions with high toxin concentrations are moving north and will continue to do so. And so you're going to have this sort of bimodal response with potentially actually decreased risk of toxin concentrations being very high in the south and then increasing risk in the north. Okay. So again, just to start to wrap up, what I've tried to show you are examples of how we have started to nibble away at this hierarchy of questions that I would posit are still quite poorly understood in the context of water quality as it relates to climate. And what I'm hoping to seed is further conversations on how else we might tackle some of these questions and how some of these questions might be really well aligned with some of the interests on the observation and the modeling side among folks at GPL as well. Going forward, some of the things that we're very interested in is moving more towards looking at coastal regions rather than riverine and lake systems, which is where a lot of our focus has been so far. This is an image from a paper that's still in preparation where we're trying to understand the relative impact of overland processes versus processes in the coastal zone itself in terms of water quality outcomes. And then I'm also referencing here a paper that we just published a couple of months ago where we looked at the MODIS archive and came up with what we think is an improved algorithm for global chlorophyll A that shows particularly large improvements in the coastal regions. And so I think that would be an interesting area for further exploration as well. And so then to wrap up, at the very highest level, I would say in terms of climate and water quality, what I'm hoping you'll take away is that really if we're talking about water sustainability, we have to include equal consideration of quantity and quality. And then the four messages I structured the talk around are that linkages between climate and water quality, and especially extreme water quality impairments, are very poorly understood. Because the role of climate is very difficult to pinpoint. As a result of this complex interplay of human activity across local, regional, and global scales, the observational evidence to underpin a long-term and global view continues to be lacking. There, as you know, a lot of new, exciting instruments are coming on board, and those will absolutely be game-changing, but we need to also think about, are there creative ways that we can infill this historical view of the last several decades? Because if we're going to be thinking about climate scale impacts, then we really need to be looking at longer term signals as well. And then, as I said, the scales of focus have traditionally been different across these scientific disciplines, and hopefully that's starting to change. In terms of the specific studies I showed here, the take-home messages are that algal blooms and also hypoxia, although I didn't show our work on hypoxia here, are becoming more frequent and more intense in many systems. Climate change is playing a key role, whether it's directly through influence on temperature and on precipitation in the systems themselves, or indirectly through its role in impacting nutrient runoff. And I show that in some of the regional and global studies that I talked about. Climate mitigation may have unintended consequences on water quality, but there are win-win options that are available to us. We just need to think about them more holistically. And I didn't show some of these figures that are here, but I wanted to mention that globally, the regions where climate change will exert pressure on water quality in terms of temperature and precipitation trajectories often coincide with the regions where socioeconomic development will also exert pressure on water quality. And so often, and again, I know I didn't show all of these global maps, the places that tend to light up in terms of where we think the higher risk is in terms of climate change itself are similar to the regions that light up when we think of them from the perspective of socioeconomic pressures. Looking ahead then, as I described, changes in precipitation have been the primary driver of changes in nutrient loading in recent decades, but warming may increasingly dominate the signal going forward. Temperature is also a key determinant of the impact of nutrients once they are in receiving waters, and I showed that with the Global Lake Study, but also with some of the coastal work that I didn't talk about today that's not published yet. Toxin concentrations, and therefore ecosystem and human health risk, respond nonlinearly to changes in environmental drivers, which complicates management and forecasting. And I also want to emphasize that although many of the studies that we do and that I've presented today really focus on extrapolating from a small number of well-studied systems to much larger geographic areas, it's important, I guess, for me to say and to recognize that while these broad studies can identify large-scale patterns, the outcomes for individual systems are still impacted by local conditions as well, and that this really poses a challenge because most systems globally are not very well and systematically monitored. Okay, I'll stop here and I'm happy to answer questions. Yeah.
Let's start with these two folks. Marie first. Wayne? You're good. You're good. Marie first. Wayne, I'll go for it.
Hello? Oh, it's just a small question. Because I know you looked at the US and globally in some form, but I was wondering if you also plan to look third world countries, different climate zones. Would it look very different, linkages in tropical areas? Is it even as relevant? I don't know much about terrestrial water, sorry.
I mean, I would say that it's absolutely relevant. I guess I'll say a few things. The main challenge is data availability, right? So maybe, actually, I'm not sure what to show. So, there was a study we did in India where already getting our hands on the data was very, very challenging. The other slight window into this that I'll say, and I'm not sure how quickly I can back up here, but in the global lake study that I showed, what was initially, so I presented this as I hope, as a nicely flowing story. But if you look at the dates of the papers, they don't necessarily align always in the order in which I presented them. When we wrote this study, what we were originally thinking that we would see is we're hoping that we could relate what we saw in these dozens of lakes globally to some of the same drivers that we had seen in our North American studies. We often did not have access to the same kinds of data sets in terms of fertilizer use rate, specific crop information, and so on and so forth. We often had some access to precipitation, temperature, and so on and so forth. What was interesting is if you go into the supplement of this paper, there's all of these plots of the many things that did not correlate at all with outcome in these lakes. And it's not so surprising, because if you think about all of these regions globally, really the dominant things that determine water quality trajectories, for example, if you look at China, right, these are all blue, indicating decrease in the intensity of phytoplankton blooms. We think this is very much due to the installation of wastewater treatment, right? Which is very different from what's the driving factor in North America. Maybe very different from, of course, what's driving things in Europe as well. And so that's part of the reason why I had this comment about sort of local conditions, of course, matter a great deal as well. And there you are data limited also. And so for better or for worse, this conclusion that I highlighted here, this, lakes that warmed the least were the only ones that fell into this first bin of sustained improvement. That was really the only clear signal that applied globally, which you can take as a positive or a negative. I think the negative is that, lo and behold, there isn't a single model that will represent the whole world, which is not at all surprising. On the other hand, it really does also show how this climate signal really is the great equalizer in some ways. So I think that partially speaks to your question as well. We did try a little bit, and maybe we can talk offline, because it would take me more than 1 minute to talk through it, but to essentially take the US-based studies that we did and turn them into more like heuristics of, these things tend to increase loading, these things tend to decrease loading, and turn these into heuristics that we applied elsewhere globally. But then it's more qualitative.
Well, first, thank you very much for amazing presentation. I guess my main question would be, do you see links that could be made with food security or health? For instance, monitoring a bacterial population in, I don't know, there's another study in like West Africa, for instance. Like, do you see potential techniques that could be used in these other fields?
Yeah, so I think the very last study that I talked about already hints at the connection to health, right? I think that, this is by no means going to answer the entirety of your question, but one of the things that is becoming possible is a much more sophisticated observation of what is happening in water from space, right? Whereas many of the studies I showed here, if they relied on remote sensing data, it's essentially chlorophyll A types of measurements, right? Whereas now that we're at the point where we can differentiate different populations and potentially signatures that correlate very well with, for example, toxin concentrations, I think that is really going to open up. It's not going to be possible to go back 3 decades, but to me, that's one of the really exciting things that may become, categorically more feasible with the advent of, PACE and some of the work that the IMIT team is trying to do and some of the other missions that are coming up later on, so that it's not just about bulk quantity or intensity, but it's really about those aspects that have a more immediate impact, whether it's on human health or ecosystem health or otherwise.
So this could rapidly demonstrate how little I know in this area.
Perfect. I love.
So in the early part of the talk, it seems like there was, trying to figure out how much, say, nitrogen got in a river or in a system.
Yeah.
You talked about how much fertilizer was being used somewhere.
Yeah.
And how much precipitation. But the notion that I get that, the precipitation washes that into the river and those two are related.
Yeah. Sure.
How much do the plants themselves mediate that? Like if it's a really successful growing season, does that uptake more of that stuff? And I didn't see any of that
Yeah.
mediation in there. Is that a factor?
Of course. So in principle, that is all folded in. So in the earlier parts of the study, we used an inventory called the net anthropogenic nitrogen input.
Oh, I see.
Net being the difference between the application and what could otherwise be accounted for by the crops that were actually produced. And then in more recent studies, there's a new, so that's the data set out of Cornell, and there's a new data set now out of University of Waterloo in Canada that's more of a nitrogen surplus, but it tries to get at that same characteristic that you're referring to. That's also part, getting back to some of the earlier questions, that's also the type of data that's very hard to get for some other parts of the world, which complicates performing these types of analyses in some other countries or continents as well.
In a natural area, can SIF be used in any way as a measure of plant productivity that would?
Yeah, you could. We did include different land cover types at a macro level, forests, shrublands versus grasslands, urban areas, and so on. That was included. We did include as candidate variables also some aspects of, so for example, tile drainage, which can accelerate the runoff of water from fields. That was included as a potential variable. So because many of these models are what I proudly would say embarrassingly simple statistical models, you can put in anything you want. And in principle, these are very empirically driven in that anything that improves your ability to reproduce the variability that was actually observed could be included. We did not test any even more classical NDVI, EVI style greenness measures, let alone SIF. To some degree, that would have been folded in partially through precipitation and temperature, because of course those would themselves be impacting the productivity. I would frankly we'd have to check. I would be surprised if those had enough of an additional explanatory power to make the cut from a statistical standpoint, just because at least for the US, spatially, it's really how the land is being used that determines most of the spatial variability. And temporally, a lot of it really is driven by this more meteorological interannual variability. But certainly we could add it in and see what happens.
I have a question, but I can hold it off.
Okay.
Make this the last question.
I think you just answered my question, but I'm going to ask it anyways. You showed a map of the continental United States, broken up into regions. It showed bright blue in the Midwest, bright green in the Midwest,
Yep.
light blue in the Southwest, and then California was kind of neutral.
Was it this one?
Yes, it was. Okay,
Yep.
that's that. So it's interesting to note that California is probably one of the richest agricultural areas in the world, and yet it doesn't show much of a change in nitrogen loading.
Yeah.
The Midwest is basically corn, some wheat,
Yep.
and it shows the worst. And I think, does this show that agricultural practices are an important variable, which kind of is modulated by climate change, but if you just use the right types of practices, you can really reduce the effect?
So thank you for this question, because it allows me to get on my soapbox and say some things that I really like saying. So taking a step back, and I mentioned this really briefly, but in the first paper we wrote, where we looked at this, which was this Eva Singha, who's a former PhD student, paper from 2016, where we looked there where we had still much less data, because these data come out every 5 years. So every time you have new data set, you have much more data. There we looked at the spatial variability and the interannual variability. And if you look at the spatial variability, what you're saying is the majority of the signal. So you see the corn belt just light right up, for example, right? And you see other regions be much less intense. So if you're asking the question of where is there a lot of nutrient loading into waterways, it absolutely maps onto intense agricultural regions within the US. In this study, we asked a different question, which is, if you look at what is shown here are the trend, so the increase or the decrease in nitrogen loading over the last 30 years, what drives that? And you're right that in this Midwest region, things are orange being an increase in nitrogen loading. However, if you look at overall changes in nitrogen input over that time, that's this map here, it's there, right? So you see some orange regions, but the impact of that is small relative to the impact of these various climatic variables. So most of what we have seen over the last 3 decades is more attributable to changes in precipitation and temperature, where precipitation changes have tended to increase loading and warming has tended to decrease loading. And I think that is useful to recognize in the context of changing this blame game that sometimes happens between the agricultural community and the environmental community. However, back to your point, we can't locally change climate back, and even globally, it's obviously going to take us some time to get a handle on climate. And so if we're actually going to improve these outcomes locally, the knob that we have is exactly what you were talking about, is exactly changes in agricultural practices. But rather than necessarily wagging our fingers and saying that farmers have made things so much worse over the last 3 decades, we can instead recognize that climate change has made it much more difficult to manage water quality. And if we were able to make this map blue enough, in other words, to change agricultural practices in a way that reduces their contribution substantially relative to the status quo, then we might be able to neutralize this effect of climate more effectively. But it puts the conversation more in a mode of co-designing a solution rather than necessarily blaming trends in agriculture, blaming trends in nutrient loading on trends in agricultural productivity, at least for recent decades and at least for the United States.
Well, what I'm saying is because California is extremely productive, its productivity actually I think is increasing, doesn't change much, but they are changing the ways they irrigate. I think they're using more drip irrigation. And maybe the message here is, I'm not criticizing agriculture, I'm just saying that there's probably some good evidence that you just change the types of crops you grow and how you grow them, you can reduce a lot of this nitrification.
So in case people online didn't hear, the question is whether we can essentially, if I can paraphrase, use California as an example of how one might use more innovative agricultural practices to mitigate water pollution. Essentially is what you're saying. I'll say 2 things. Certainly, also as I was saying a minute ago, the way to locally address the impacts of global climate change, so global human action, is by changing practices locally. But I also want to point out that California, relative to the Midwest, is a very, very arid place that is tending to get drier rather than wetter. And so if you look at this climate piece, right? So this has nothing to do directly with the agricultural productivity, but just to how have changes in rainfall and temperature impacted things. You can see that California is just, barely yellow as a result of, again, you can break it down, right? Precipitation and annual precipitation. And so the lack of a large increase in nitrogen loading in California is also partially due to the difference in the climate change trajectories that have been experienced in California relative to the Midwest, where you're really seeing both more rainfall overall, but also more intense rainfall events in the springtime, which also tends to coincide with fertilizer application timing, when the soils tend to be bare and therefore more prone to stripping of nutrients and so on. Okay,
we're going to call it there because we've got other groups coming in, but I'd like to thank Anna again. I have a question for you, but we'll do that after. Sure. Let's thank Anna again for a fantastic seminar.
And I'm not sure if there was any questions online, but I'm happy to just type out answers later.